Okay, let's jump on this horse and ride. We need to cover a review for exam 2 on chapters 4 and 5 today. I think we got plenty of time, so don't hesitate to stop if something is confusing you, or if I'm confusing you. What I'm going to do is I'm going to take the review document that I've posted in Blackboard and work from that. I've picked out several of the questions from the review document to give us talking points. All right, so let me share that document, and let's see. Here it is. All right. Tell me if that's not visible. Should be exam 2 review. Actually, the key for that review. And let's see. As it turns out, I picked the whole first page. All right, so the thrust of these 2 chapters has been working with chemical foundations, but eventually, in chapter 5, we get into nomenclature. Nomenclature is like it's the pivotal point for chemistry. You can't name your compounds, you can't write your compounds from the name, then there's no point in continuing, because that means you either don't know the symbols, you don't know how to put them together, and that will just kill anything that you want to do in the future with chemistry. So let's get started. Number 1, I'm not going to write on the board unless I have to. Number 1, the symbol for the element iodine, which should be fairly simple. Iodine is one of those elements that has claim to a single letter for its name. So that makes D the only logical choice. There are, let's see, these other symbols. I'm pretty sure IN is indium. IE, ID, and IO are fictitious. So I is the symbol for iodine. Then you have those like number 2 that don't follow from the English, right? They're derived from the Latin words. So lead, in fact, there's no element with L, and there's no element, there might be one with LD or LE, but P is phosphorus. Lead is PB. Remember, you always have to have a capital letter followed by a small letter if there are 2 letters. And PB stands for plumbum, Latin for heavy. How about the next one? This one is a little more cryptic. Which of the following elements is an alkali metal? So you got to know where the alkali metals are. You will have a periodic table available. And I would suggest that before you go into a lockdown browser and take the exam, you should go into your normal browser and find the exam folder and look for useful information documents that are in there with the exam. And you can print those off. That's just to be sure that you have access to them, because when you go into Lockdown Browser, it may not let you open those documents. So you need to have them with you. It's okay. I think the way I've constructed it is the Lockdown Browser, the useful information document is a single document with the various pages in it. Okay. So be sure you have that useful information document with you. And it's kosher to use anything that's in that document. And it should have a periodic table. Also in the Lockdown Browser, in the Lockdown Browser, when you, if your calculator, the battery goes dead or it stops working, the keypad's messed up, there is a scientific calculator that's available in Lockdown Browser. You just look at the top border and you should see a little icon for a calculator if you need one. Okay, so let's go back to this question. Which of the following elements is an alkali metal? So all you have to do is, you know where your alkali metals are, right? They're the first column, and you just match it. Which one is there? I mean, if you don't remember, like I remember, that's sodium. Sodium's an alkali metal, and none of these other guys are. AU is gold, SC is scandium, SR, the gold and scandium and cobalt down here are all transition metals. They're in the middle part. SR is strontium, and that's an alkaline earth. It's in the second group. Okay. So you should be able to find sodium, or actually you should know the name for Na, which is derived from the Latin natrum, which means sodium. Okay, so number 3 is, the answer is D. Let's say an atom with 45 protons has a mass number of 100. How many neutrons will it contain? You just need to remember the definition for the mass number. The mass number is protons plus neutrons. So if you're given the protons, you subtract it from the mass number and you get the neutrons. So that should be 55, correct? 45 and 55 is 100. What's the most abundant element in the human body? And that's probably not a very good question, because what do you mean most abundant? I mean, is it most abundant by numbers of oxygen atoms, or is it by mass? And in this case, I would assume mass would be correct. First of all, the human body is over 60% water, right? H2O. So there's a clue right there that oxygen is the most common element in the human body, most abundant. How about CO? I told you that one in a previous problem, didn't I? CO
So the
stands for
last answer was oxygen?
Yeah.
Okay.
Yeah. Oxygen's the most common element, most abundant element in the human body. CO is cobalt. Right, so that one follows. CO, you can derive that from cobalt. All you have to remember is that C by itself is already taken. Right? C by itself is carbon. So anything other than carbon has to have 2 letters if it's going to use C as the capital. Then CO is cobalt. You have lots of elements with C in it. Calcium, copper, let's see, chlorine, but they all have to have 2 letters because carbon's already got 1 letter. So A is for 7. Let's see. I'm just going down the line. I better check my table. I didn't have that one marked. I do have 7 marked, and I just gave you that one. Right? The symbol for copper is Cu. for cuprum, right? And always remember, if you write an element with 2 capital letters, it's wrong. That's just the rules. Second letter always has to be small. Right, copper derived from cuprum means Cu. Let's see, let's go down to 10. I didn't pick all of them, of course, because there's so many. Like, what, 180 something questions in this document. You know, we wouldn't have time to go through all of them, so I picked ones that I thought were representative and useful. 10. Okay, let's say I could shut the sound off of this phone. 9 o'clock, the junk calls start. An atom has 54 protons, 54 electrons, 78 neutrons. What's the element? Which one of those do you need, really, to tell you what the element is? You only need the protons. Different number of protons means a different element. The rest are variable, right? If the number of electrons is different from the number of protons, what do you have? You have an ion. If the number of neutrons is different for two of the same element, that's an isotope. So 54 protons. You just take your periodic table, and it starts from small numbers at the top going down and across. So you just follow it down till you find 54. And it looks like that's xenon. Xe for xenon. Let's see. Let's go to 12. How many neutrons are there in one atom of Sc 4521? That's kind of the same question as you had before. 21 from 45 is 24, correct? So that means 24 neutrons, because the mass number is the total of protons and neutrons. 13, which of the following is a noble gas? So you got to know where the noble gases are on your periodic table, right? Over here to the far right, and just find the one that matches. Noble gas is argon. There's another clue in here also. Test-taking technique for multiple choice questions. If you know that noble gases do not form compounds and do not combine with one another to form molecules, then you know that the only possible answer in there is a single symbol, right? Ar, argon. That's a diatomic, and a molecule, compound. So none of those could be, because the noble gases are all single elements. They don't play well with others. Okay, 14. The chemical formula Al2O3 indicates what? Well, first of all, what elements do you have? Al is aluminum, O is oxygen, right? So which one of these satisfies? Let's see what it's asking. Atoms of aluminum and oxygen, it looks like. So you count the number of each. So you're going to have 2 atoms of aluminum and 3 atoms of oxygen. So C is the only possibility there. Well, it's not the only one, but since you found a correct one, then E is wrong, right? It couldn't be E, because there is one correct one in there, and that's C. Let's see, 15, yeah. Si. That's the symbol for what? It's the foundation element for our semiconductor industry. Without that one, you wouldn't have cell phones, televisions, computers, any of that neat electronic stuff. You could have the electronic stuff using a different basic element for the semiconductors, but the alternatives to silicon, while they can perform the same duties, are much, much more expensive. Silicon's used because it fits the bill, plus it's cheap. So that makes C the answer. Okay, let's see. 17. How many of the following did Dalton not discuss in his atomic theory? So now we have to know what the atomic theory for Dalton says and look for those things that don't fit, right? Did he say anything about isotopes? No, he had no clue what isotope. In fact, Dalton's atomic theory was the beginning of understanding of the behavior of elements and formation of compounds and chemical reactions. So we hadn't even arrived at the point when Dalton was active of understanding the structure of the atom itself. The atom was as simple as he could go. That's as far as the science would allow him to go, was the atom. He just took the ancient Greek theory of the atom being the foundation for all matter and fixed their problem, right? The ancient Greeks thought that everything was made of the same atom, an elementary particle that was the same for every substance. So they painted themselves into a corner there, because if all the atoms are the same, how come we have different substances? And they really never figured that one out. What Dalton did was he said, all right, I'll go with elementary particles called atoms, but this element has a different atom than that element. And that solved the problem right there. He didn't know why they were different. He didn't know about protons and neutrons and electrons. He just, that was foundational to his theory, right? So he didn't know about isotopes. He didn't say anything about ions either, right? Nothing about ions. He said nothing about protons, electrons, or neutrons. He didn't say anything about these guys right here. So all 5 of them are absent from Dalton's atomic theory. That's why B is the answer. Okay, let's skip down to 20. The number of neutrons in Be. First of all, what's Be? It's beryllium. So you got to find beryllium on your periodic table. It's right up here. It's at the top of the alkali metals. The alkaline earths, pardon me. Alkaline earths. And it has a atomic number of 4, so it has 4 protons. How many neutrons does it have? Well, that's really not a good question, because we know about isotopes, right? It could have, and does, in nature, have a mix of isotopes. But I think what we're getting at here is the most common number of neutrons, right? So if you look at the atomic mass up here in the top of the square, it says 9.0128. Okay, so remember, when we do these calculations for atomic mass, it's a weighted average of the isotopes. And the number here is going to be closest to the most abundant isotope. So what's the most abundant isotope? To give you 9.01, it would be 9. 9 would be the most common isotope for beryllium. Okay, now if you assume that as the mass number 9, then 4 from 9 is 5. So you would expect 5 neutrons. And in addition to that, let me write that up here. Beryllium 4,9 is the most common isotope, and that's number 20. The most common isotope. What's the next most common? Well, think about the weighted average is a little over 9. So it stands to reason the next one is probably 10, right, with 6 neutrons. And it's a very minor component because the weighted average is so close to 9. Then if you look at the selections, what do you have to select from here? Well, 10 can't be it, right? That's because then you'd have to have a 14 as a mass number. 5, we think, is probably it, this one. This one would have 6, right? There's no 6 there. So if you use logic from your atomic mass being just a hair past 9, then if you would say this one, you would expect to find 6 as the answer, and it's not even there. Okay, is that, I hope that's clearer than mud. All right, 2021. Which of the following is a non-metal? You got to know where the non-metals come from, right? And on your chart, there's a black line that zigzags. It goes to the left and underneath boron, and then it stair steps all the way down. It doesn't skip 2 steps, right? It goes 1 step at a time and zigzags all the way down. To the right are the non-metals, to the left are the metals. So all you have to do is find out, and you have to know the symbols, right? Because your periodic table won't have the names. That kind of defeats the purpose of testing, right? If you have the names right there, then what's the incentive to memorize them? So you look at your choices, right? And you just take them one at a time and say, carbon, where is it? Carbon. Carbon's right there. It's a non-metal. You can stop. You found your non-metal. The rest of them have to be metals. Cerium, cesium, calcium, copper, all metals. And if you got the time and the interest, you can look for them. You find them all over here. All right, 21 is done. 23, take a look at 23. Here's another question about Dalton's atomic theory. So, which of the following does Dalton's atomic theory not address? And here we're given examples. Right? So what we want is 4 of them to be true and 1 of them to be false, because they're all unique answers. You don't have any of these, none of the above, all of the above, 2 of the above, that kind of thing. So that being the case, only 1 of them can be wrong. So let's look. Is A true? Hydrogen and oxygen gas combine to form water. Yeah. Dalton explains why that is. What he's saying is, and this part of Dalton's theory addresses that, he's saying that you don't create atoms, you don't destroy atoms, you just rearrange atoms. So when you have hydrogen on one side, now he didn't know this, what I'm going to write up here, but this is derived from what he was talking about. He says hydrogen combines with oxygen to yield water. Okay, now that's not balanced. We haven't done equation balancing yet. I'll go ahead just to keep my head straight. We need 2 of those and 2 of these. Okay, so what he was saying was, they knew at that time that this was an element and that was an element, and this was a combination of those 2 elements, because they knew how to break them apart and find out what it was composed of. So he was saying that, sure, combine that one and you get that one, but you still got these elements in that product. They're just rearranged. So A is definitely true. H2O2 consists of 16 grams of oxygen for every 1 gram of hydrogen. He incorporated into his theory the law of definite proportions, right? In fact, that was his creation. So if he's going to make a theory, he better stick his own laws in there. And he said that H2O2 consists of this combination by mass, right? At this time, they didn't know about, well, they knew about elements and atoms in his theory, but they didn't know about the exact combination of atoms like this that were responsible for this mass ratio. What he was just saying was that the ratio of oxygen to hydrogen is 16 grams to 1 gram always, no matter where H2O2 comes from, the hydrogen peroxide. Whatever its origin, it's always that combination. So yeah, he did address that one. The relative mass of carbon atoms is about 12 times that of hydrogen. Right? They knew that too. See, what he was trying to do was, in his theory, he was trying to explain, and that's what theories do, say why all these other laws that preceded it were correct, why they worked, right? Laws don't say anything about why, but his theory did, and incorporated all of these various laws into his explanation for why they work. This one's pretty simple. The seat you're sitting on is made of atoms. Yeah, all matter is composed of atoms. That was like his foundational statement. What about hydrogen ignites in an open flame, but helium does not? Well, that may have been true and they understood it, but it wasn't part of his theory. Right? He didn't try to explain that in his theory. So really the only one that doesn't fit is this part about hydrogen ignites, but helium does not. Okay. Let's see. 23. The symbol for the element mercury. Right? That's one of those that doesn't follow from the English. I mean, mercury is not Me or Mr or My. Mercury is Hg. And I think it's the Latin word for Hg is hydrogenium. It's water forming. I think that has to do with the alchemy that had preceded modern science in terms of hydrogen. Actually, water forming. I'm not sure about the chemistry they used, but they selected that as the foundation, the Latin for the derived symbols for the name, Mercury. What does N stand for? It's one of those privileged few that get to have one letter. N is nitrogen. Anything else has to have two. Nickel would be Ni. Nobelium, let's see, nobelium I think is N. Logic would say No, but I don't think that's right. See, I don't have all of them memorized either. These are actually I think this was a man-made element, nobelium. Niobium, I think that one's Ni. No, not nickel, not Ni. I think that one's Nb. Neon is Ne, right? So nitrogen is the correct answer. 26. Oops. Choose the pair in which the following have the same charge. Okay. Let's see, what do we mean by that? The same charge. Do we mean the same sign and the same magnitude? Let's see if one fits. Hydrogen atom and an electron. Well, hydrogen atom's neutral. Electron is -1, so that can't be it. An electron and a neutron. Same problem. Electron's a negative charge, neutron's neutral. A neutron and a hydrogen atom. Yep, they have the same charge, like they had no charge. Neutron is neutral, hydrogen atom is neutral, because one proton and one electron cancel one another. So that would be a good answer. Proton and a hydrogen atom, nope, proton's positive charge. Proton and neutron, oh, proton's positive charge. So yeah, C is the best answer. They have the same charge, which is 0. Let's see. 28. 28. The number of protons in the nucleus of an atom is called its what? Atomic number. Right? We know that the atomic number is the same as the number of neutrons, but when the atomic number was first proposed by Moseley, it was not, the correlation between the atomic number and the number of protons was not established yet. Remember, Moseley was doing X-ray spectrometry with elements and found that he could predict the wavelength of one particular emission. He could predict that wavelength with a formula, and the only thing he had to change from one element to the next was a multiplier, an N number. And it was a whole number, 1, 2, 3, 4, 5, 6. And he found that his elements, they fit in the chart, right? And they were sequential, right? This one would have an N for his formula of 26, and cobalt then would have a 27, and nickel would have a 28. So he discovered the atomic number before they knew what it was related to. Now we know that it's equal to the number of protons. Okay. What was that, 28? No, 28's B. Okay. 29. Which atomic particle determines the chemical behavior of an atom? All right. Think about when atoms approach one another. They haven't reacted yet. They could be part of a compound, but for simplicity, let's say just two independent atoms approach one another. Let's see over here. And they come together. What's the first thing they see? The first thing that interacts between atoms is their electrons, right? Because they're way out here. The neutrons never get really close to one another. They're always separated by a distance because they're positive charge. The interaction of the electrons forms the bond. And that seems kind of counterintuitive, doesn't it? Because electrons are all negative charge. So why wouldn't they, all atoms just repel one another and we'd have a universe of independent elements, just all free atoms? Well, good thing it doesn't work that way. The only time nuclei interact is when you really force them to, like in the core of the sun. Then you get nuclear reactions, not chemical reactions. Chemical reactions are governed by the interaction of electrons. Actually, it's not just the electrons, but the space that they occupy, the orbitals that interact. And it's almost like the electrons are there along for the ride, but not really. So I'm complicating things. Let me stop that discussion right now. So that was 29 is B, electron. That's what determines the chemical behavior of an atom. 30. What's the most abundant element on the Earth? In the crust, oceans, atmosphere, all combined, same as the human body, oxygen. Think about it. That's why this question, I've wanted it specified not just the crust, but the oceans and the atmosphere. Right? The atmosphere is 20% oxygen. The ocean's composed of water, which is, what did we say earlier, 18-to-1 ratio of mass of oxygen to hydrogen. The crust of the Earth, most metals in the crust form compounds, which to a large extent includes oxygen as a combination. Many of them combine with other elements like sulfur, but oxygen is more common. So oxygen is everywhere. While we're on the topic, what's the most common element in the universe? Hydrogen. Hydrogen fuels the stars, as they say. Okay, 31 is on my list. An atom with 15 protons and 16 neutrons is what? We did one like this earlier. The number of protons determines the element, right? So you go to your periodic table and you look for 15 protons, the atomic number of 15. Turns out to be phosphorus. Okay, let's skip down to 33. Okay, this is going to require a little detective work. So let's extract information from this problem and put it up on the board in a different format. Okay, we have a certain isotope that's our placeholder symbol, X, and it has a charge on it. So it's an ion of the element. This ion has 37 electrons and 73 neutrons. Okay, that's given. What's the mass number for this element? All right, what goes right up here? What do we know? Well, we know the number of neutrons, right? That goes into the calculation for the mass number. But we don't know the protons yet because we don't know the element. So how many protons are there? What's the charge? 2 plus? That means you have 2 more protons than electrons, right? The imbalance is toward the protons. So if you have 37 electrons, that means you have 2 more protons than that. You have 39 protons. Okay, now we can calculate. So that's 2 and carry the 1 and 11, right? Right, 112 would be the mass number. By the way, what element is that? Let's see. 39. That's yttrium. I don't know if you had to, I think you might have had to memorize that one. Yttrium. But it's not just yttrium atom, it's an yttrium ion because of that charge. All right, that was 33. Let's go to 37. Okay. So 37 says, how many phosphorus atoms are represented by one formula unit of cobalt-2 phosphate? And I was kind here. I didn't make you write out the formula. I just wanted to see if you knew how to read the formula. Cobalt-2 phosphate is CO3 see, 3 times 2 says 2 times 3. There we go. It should be a 2. Yeah. So how many phosphorus atoms are there? Well, you've got this polyatomic ion in here with one phosphorus per unit, but you've got 2 units, right? So you have 2 phosphoruses. That's why the answer is A. How about 39? How many atoms are represented by one formula unit of aluminum chromate? Now this is how many total atoms. Let's see. Aluminum chromate. Aluminum and then chromate has a 2- charge. This is a 3+ charge. So that means cross multiply a 3 down here and a 2 down here. Okay. So how many total atoms? Well, we've got 2 plus 3 plus 12. Should be 17. Okay. All right, let's see. Do I want to look at 40? I think I probably do. Yeah. Okay. Which of the following statements are true? So more than one could be true. We just have to find out which one it is. Okay, Roman numeral 1. Models are always wrong unless they are proved by a theory. No. Models are derived from a theory. You establish the theory, and then to expand it or expound upon it, you create the model based upon the precepts of the theory. So if a model is wrong, then the theory is wrong, right? It's not wrong unless you're proved by a theory. It doesn't work that way. They go hand in glove, like hand in glove. So 1 is false. How about 2? Elements such as lead are made of tiny particles that mostly consist of open space. That's about as true as you can get without saying exactly what lead is. As an example, any element is made of tiny particles, now we call atoms, and they are mostly empty space. Rutherford proved that with his gold foil experiment. Right? He fired alpha particles at gold foil, and most of them just went straight through. No deflection at all. But some of them were bounced off in different directions. And that's how he proved that his nuclear model for the atom. Most of the mass of the atom is in the nucleus. And the rest is empty space. Well, not empty space, but nearly empty space occupied by electrons, which have virtually no mass. So 2 is true. All right, so test-taking technique, look at your choices. If 2 is true, then A, B, or C could be true. All of the above can't be true because we found a false one already. So A and B and C are possible. So let's see what 3. 3 would have to be false, right? Because it won't fit in with 2 that's true. The air you breathe is an example of a heterogeneous mixture? No, right? Any mixture of gases is homogeneous, always. That is, mixtures of gases form a solution, a homogeneous mixture every time. So 3 is false. So let's see. If 4, since 2 is true, if 4 is true, then we found that B is the answer. Can't be C, because 1 is false. So let's see, what about 4? Because NH3, which is what? NH3 is ammonia. Since that always contains the same relative number of atoms, it will always contain 4.6 grams of nitrogen for every 1 gram of hydrogen. Well, you may have to do some calculations, right, NH3. So, what mass for nitrogen there? Well, if we look at the periodic table, it says it's 14.01. But hydrogen, there are 3 of them, right? So if we look at hydrogen, it's 1.01, but there are 3 of them. So it's 3.03 total. Oops, 3.03. So there's your ratio. 14 to 3. Right, so that's the wrong ratio. No, it isn't. Hold on a second. What's 3 into 14? Is it about 4.6? Yeah, okay. 4.6 to 1, right? I heard a ding. No, okay. I was looking to see if Melinda showed up. Nope, don't see her. Okay, so that ratio is correct. And we got the ratio from the atomic mass of each one. This one is only 1, so it's just that value. This one's 3 of them, so it's 3 times the value. That ratio will be consistent no matter what the source of ammonia. Whatever the derivation, doesn't matter. If it's ammonia, it'll always have that ratio. So that means that 2 and 4 are both true. That's why B is the answer. All right. Let's see. All right, we're doing good on time. 42. Take a look at 42. Which of these pairs have approximately the same mass? And we're saying approximately. They're not identical. They're very close. How about a proton and a neutron? Oh, yeah. The neutron is just ever so slightly more massive than the proton, but not much. So that answers the question. Electron is 1,800 times less massive than a proton, so B can't be it.
a hydrogen atom and a deuterium atom. What's the difference there? Well, hydrogen is like this with no neutrons, right? That's the most abundant, the most common isotope. Deuterium is this one. Let's see. Excuse me. 1, 2. There we go. And then you got another one like that. Those are the 3 common isotopes of hydrogen. And the hydrogen atom and a deuterium atom. Okay, what we're saying here is the hydrogen atom is the most common one. Or actually, it could be the average hydrogen atom, right? So we can't say that this one is the same as that one. We're specifying this one to be that isotope. But the hydrogen atom, we're typically saying it's this one. But even if it were a combination of all of them, it would still be less massive than this one, because this is the most common one. A neutron and electron, well, no, they're about 1,800. Electrons about 1,800 times smaller. Hydrogen atom and tritium. So that's comparing this one and that one, right? Same problem with C. That's why A has to be the right answer. 43. How many nitrogen atoms are indicated by the formula Al in parentheses NO2 taken 3 times? By the way, what is that? What's the name of that compound? Let's see. 43. Al NO3 taken 3 times. How would we name that? Well, what type of compound is it? Type 1, 2, or 3? It's not a type 3 because you got a metal and a polyatomic ion. So it has to be a 1 or a 2. Well, aluminum, is it a fixed charge? Yeah, it's a fixed charge, so it's a type 1. That means you only have to name aluminum. You don't have to say what charge it is. We already know what the charge is. And then this, what's that polyatomic ion? Well, there's a table. It should be useful information with polyatomic ions on it. Right here. Right there. And you look it up, NO3, look on the right-hand side, because that's in order of the symbols, and you find that this one is nitrate. That's it. That's the name. Type 1 compound. But to answer the question, how many nitrogen atoms are there? Well, there's 1 per group, and we got 3 groups. So you have to have 3 nitrogen atoms in that molecule. That's why E is the answer. You have 3. All right, let's see. Lost my place. Let me go back. 43, 45 next. Which statement below is incorrect? All right, now we got this ringer E. At least 2 of the above statements are incorrect. So if we find one that's incorrect, we're not done yet because we got to eliminate E. If there's only one that's incorrect, then that's the answer. But if there are 2 that's incorrect, then E is the answer. So we got to find out which ones are incorrect out of all these. O3, ozone, is considered a molecule, but is not considered an element. Is that true? Well, it is a molecule, right? It's got 3 oxygen atoms bound tightly together with covalent bonds, and it behaves as a single unit. But is it not considered an element? No, it is an element. Ozone is a molecule, and it's an element of oxygen. In fact, it's got a name. It's one of the allotropes of oxygen. An allotrope, remember, is an element that can take can have different formulas. I think in the class I used carbon as an example. Right, you can have graphite with its arrangement, its hexagonal arrangement in sheets. You can have diamond, which is a tetrahedral arrangement in continuous infinite array. Right, that's why it's so hard. You could have fullerenes. A Buckminster fullerene was one of the earlier ones. It's a C60. 60 carbons in this spherical arrangement. They call them buckyballs. And nanotubes, which actually go on forever. They could have an infinite number here, because they're just tubes, and they go this long or that long or that long. So yes, it is an element. That makes A false because of that statement. Not considered an element? Oh, it's an element, all right. How about B? Gases behave the most ideally at high temperature and low pressure. Well, you know why? I don't know why I stuck that one in there. We haven't spent a lot of time on gases. Okay, I'll just tell you right now. That's true. Gases behave ideally at high temperature and low pressure. So they're moving really fast and they're far apart. So you have to take my word for it at this point. I'll explain it later when we get to chapter on gases. C, 1 mole of aluminum is equal to the number of aluminum atoms in 26.98 grams of aluminum. What do we mean by a mole? Well, we mean 6.022 times 10 to the 23rd atoms. And how much will that many atoms of aluminum weigh? You look at the periodic table. The atomic weight of aluminum is 26.98, which means that if you have that mass of aluminum in your hand, you have 1 mole of aluminum atoms. So C is true. How about D? Dalton's statement, all atoms of a given element are identical, is no longer accepted because of the existence of isotopes and ions. That's true. Right? They're not identical anymore. And that statement in Dalton's theory is not accepted because of that. So that means there's only one false one in the whole group. That's A. All right, let's go down to 48. We're good. We've got a couple hours left. How many protons are in the atom carbon? Just look at your periodic table. Where would you find that information? It's the atomic number, right? And in this table here, it's in the lower left-hand corner of each of the squares. So you look for carbon. Carbon has atomic number of 6, which is the number of protons. That's 48. Let's skip down to 51. The symbol for SN stands for the element what? That's one of those Latin terms. SN is from the Latin stannum, which means 10. What's the significance of 10 historically? You ever wondered about that? Well, right. In modern times, we had tin cans, like that steel, and they dipped them in tin, right? And what the tin did was it protected the steel underneath from rusting. But before that, tin was used as an alloy, and it was combined with copper. And in the proper proportions, tin and copper makes bronze. And bronze is more durable and stronger than copper. So in ancient times, much of the chemistry that was discovered and used and learned had to do with wars. You know, you fight your enemies with weapons made of different things, right? In the Stone Age, of course, you made spears with flint heads tied to the end, flint points, or you hunted with it. So it's not just war, I guess. It's the history of weapons, let's put it that way. And then you progress to deposits. Free elemental copper was identified. And then it was learned how to smelt copper from minerals. And you had to have the command of fire to do that. So they smelted copper ores, and they made copper, made their weapons out of copper. And all your enemies, their weapons were made out of copper. So when you clashed, the technology was sort of balanced. And then one civilization figured out how to mix in some tin, make an alloy, and their bronze was stronger than copper. So you met your enemy in battle, and when they swung at you with their swords, you swung back with your bronze and just chopped the top off of their swords. And then the Bronze Age came to an end when iron was discovered. Now, when you smelt iron from its ore, it takes a much, much higher temperature. It's very difficult to do. But once you accomplish it, and you can hammer your weapons out of iron, then you can meet your enemy with bronze swords and chop their swords in half. Well, that wasn't good enough. Then along came civilizations that learned how to incorporate a little bit of carbon in their weapons. No, not just incorporate it, but control it. That's the key. Control the amount of carbon. And they made steel. Then they could come at their enemies with iron swords and chop theirs off. Okay, so tin was historically significant as an additive, an alloy with copper to make bronze. Okay, let's see, 55. How many protons, electrons, neutrons does 45 Sc2+ have? Yep, 45 Sc2+. All right. So how are we going to do this? How can we determine the number of protons, electrons, neutrons? We don't have an atomic number for this element here. Is it available? Yeah. Once you know the symbol and the name of the element, you just find it. There it is, scandium. It has atomic number of 21. Right? So if we got to have protons, electrons, neutrons in that order, protons, electrons, neutrons in that order, then protons would be 21. How many neutrons? 24. Okay. How many electrons? Well, how do you get a 2+ excess? Can't change the protons. You have to change the electrons. So you subtract 2 electrons and you get an excess of 2 pluses. So that means you have 19 electrons, 2 less than the protons. So you just look down here and find the one that fits, 21, 19, 24. There it is right there, B. Okay? All right, 55, let's skip over to 61. There's a lot of repetition in here, and I do that for a purpose. The best way to learn chemistry is to answer questions and work lots of problems. And I've said it before, and I'll say it again. Your two best friends in chemistry are curiosity, want to know more, and boredom. If you're bored working these problems, that means you know them. Okay, 61. The average mass of a boron atom is 10.81. Right? That could be atomic mass units. Well, in this case, boron atom, 10.81. Yeah, it would be 10.81 atomic mass units for boron, because we specified boron atom. Assuming you were able to isolate only one boron atom, the chance that you would randomly get one with a mass of 10.81 is what? How likely are you to find an atom with that mass? 0%. That is a weighted average of the naturally occurring abundance of isotopes of boron. It does not represent a single atom. That's kind of a trick question, actually. Just see if you're paying attention. Okay, let's go down to 65. Which of the following elements is most similar to chlorine? Right. So this is, well, Mendeleev wasn't the only one, but he popularized the concept of groups or families of elements with similar chemical behaviors. So which would be most similar to chlorine? Any element in that group, right? Any of the halogens, right here. Any of the halogens will fit. So you find, is there another halogen in that group? Let's see. Helium's not. That's a noble gas. Mercury, that's a metal. Hydrogen, hydrogen is a universe unto itself. Sodium, now that's an alkali metal. Bromine, Br. It's the next heaviest one in that family, just below chlorine. There you go. Bromine, E is the answer. Let's see. Okay, now let's skip over to 70. How about this one? This one is actually easier than the earlier one. How many protons, electrons, neutrons does 31P have? So you just look at your periodic table. You find that P has 15 atomic number, which is 15 protons. So it'll be A, B, or C. And then you find electrons. It's a neutral atom. So the electrons will be exactly the same. So now it's B or C. And then you say, how many neutrons? Well, it's not 31. That's the mass number. That's a total of protons, neutrons. 16 is the difference between 31 and 15, 16 neutrons. So C is the answer. All right, 71. Which of the following contains the largest number of oxygen atoms? Okay, so you've got two things operating here. You got the formula, and you got this coefficient that says how many of those formula units do you have? So for water, you have one oxygen per molecule, but you have 4 molecules. So that means you have 4 oxygens. It's the number of oxygens. Right? How about this one? Oh, 3. You've only got one of them, and they're 3. How about this one? H2SO4. You've got 4 oxygens Only one molecule, so that's 4. And 3 CO2s, carbon dioxide, you have 2 for each molecule, but you have 3 molecules, so that's 6. And then we have aluminum nitrate. We wrote that one earlier. Right? So you have, in the nitrate, you have 3 oxygens, but you have 3 of the nitrates in the molecule, which makes 9 oxygens. Right? So the one with the largest number of oxygen atoms is aluminum nitrate. All right, 72. Let's see. 72. How many atoms of oxygen are in one formula unit of calcium dihydrogen phosphate? Okay, now we're getting tricky. I'm not giving you this one. Calcium dihydrogen phosphate. Dihydrogen phosphate. All right. So you got to be able to write the formula. Otherwise, you can't count the number of oxygen atoms. Right? So we know we have calcium. By the way, is this a type 1, type 2, or type 3? Calcium's metal, so it's a 1 or a 2. Calcium is an alkaline earth. It's in the second group, always has a 2+ charge. So that's a type 1. Dihydrogen phosphate. If you haven't been studying the polyatomic ion list, you may miss that as a polyatomic ion. So dihydrogen phosphate is this, right? And it has a -1 charge. Okay, look it up. So if we're going to balance a 1- and a 2+, we can't mess with that formula for the ion. So we need 2 of them. Now we've got our formula. Now how many oxygens do you have? 2 times 4 is 8. That's why the answer is D. All right, let's see. Skip to 75. All right. Which of the following statements is true? All right, this one's gets kind of messy. A, B, C, D, E choices. 1, 2, and 3 are all false. So that means none of them are true. Only 1 and 2 are true. 1, 2, 3 are all true. 2 and 3 are true. 1 and 3 are true. So you got to look at each one and decide which ones are true and which ones are false. So we got Roman numeral 2, 1, 2, and 3. Okay, so let's look at them. True or false? The number of protons in an element is the same for all neutral atoms of that element. Is that true? Yep, that's true. As long as it's the same element, the number of protons is the same. So this one is true. How about 2? The number of electrons in an element is the same for all neutral atoms of that element. That's true, because if it's neutral, the number of protons balance the number of electrons. So that one's true. Okay. 3, the number of neutrons in an element is the same for all neutral atoms of that element. False, because we know of isotopes now. You can have different numbers of neutrons and have the same element. So that one's false. Only these two are true. So that means only 1 and 2 are true. B. B's the answer for that one.
I got a quick question on the periodic chart.
Yep.
Because I see that I was looking at the one that you sent us online.
Oh, with the red boxes and stuff?
Yeah, what does the red boxes represent? Because I was trying to make my flashcards and I was going to put, like, is the red ones the ones that we just need to learn?
Yes, yes.
Okay.
Only the ones that are boxed in with red. Sometimes it may be a box around one element. Sometimes it's a red box around a group of elements.
Okay,
All,
I see it.
everything inside the red is memorizable.
Okay.
Right. And then the ones that are highlighted in the background with blue, those are your diatomic.
Gotcha.
Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all written as diatomics at 1 atmosphere pressure and room temperature. Those are all diatomic, so they'd be written like this. Always. And that's important because if the word problem says react, or you're going to react methane with oxygen gas and produce carbon dioxide and water, and you write those out in words, and if you have to write the chemical equation for that reaction, and you don't write O2 as the oxygen, then it'll be wrong. It'll never balance. So
and with the exam, will we be allowed, if I did make my flashcards, to use the flashcards?
No.
Okay.
Just the useful information that's provided in that folder with the exam.
Okay. And then with the this part right here, is that the group that it is? IVA, VA.
What about it?
What is the IVA and the VA? Is that just Roman numeral?
Those are the group numbers.
Okay.
And notice there are 2 different types of group numbers. The ones that have the Roman numerals is the old system. The ones that have just numbers across the top, from left to right, 1 through 18, that's the new system.
Okay.
Okay. We'll talk about that a little more when we dig into the periodic table and its structure a little bit later.
Okay.
You would only need to know those numbers 1 through 18 if you're going to fill out the extra credit periodic table. I think, is that available for this?
Yeah, it is.
Okay. So for that one, when you put the numbering system across the top for the groups, use the new system 1 through 18.
Okay.
I think I specify that in the instructions. Use the.
Is there a due date for the extra credit?
Yeah. Let's see. I've got, let me look. It's in my. Did I not put it there? Okay. 11th, February 11th. That must be. That's the day of the exam too.
Okay.
The reason I did that was these extra credits are designed to help you memorize the elements, learn the structure of the periodic table, and name compounds. That's the other 50 ways to know your compounds, name your compounds. You have 2 extra credits. And if you don't do those before exam 2, then it's kind of a waste of time. because the
Yeah.
whole purpose is to get you to memorize those symbols and learn how to write compounds, and that's what the extra credit is for. Besides that, give you extra points. Okay, 75 is done. Go to 76. Here we go. So 76, correct formula for carbon monoxide. All right, type 1, type 2, or type 3? Two nonmetals, type 3. So that means charge is irrelevant. You just name the compound. You write the compound from the name based on how many of each of the elements are given. Carbon monoxide. Carbon, since it's first, doesn't say mono. It's just one carbon. And we say how many of the oxygens are in there. 1. That's it. You're done. Answer's B. Now this one, I put this one in here, number 77. The reason I put that one in there is because it may have been confusing. I consider a binary compound where you have 2 parts. And the parts can be polyatomic ions. But your authors in the book, they consider binary compounds only 2 elements. Okay? Well, first of all, which of these are compounds? Right? You have to have 2 different elements or more to have a compound. Right? So that lets oxygen out. D cannot be a compound. The others are compounds because they have 2 or more different elements. Now, are they binary? Well, from my definition, all the rest of them are binary. But the authors in your book say that they have to be 2 elements. Right? So by that definition, C is the only binary compound in there. It's got hydrogen and sulfur. That's it. Okay. So to answer this question, you have to use the author's definition of binary compound. Okay? And test-taking technique. I mean, if you look at the possibilities, and you eliminate oxygen, of course, and there has to be one of them right, the best one is going to be the simplest one. 1 hydrogen, 2 hydrogens and 1 sulfur. That's the way I would approach it. 79. The correct name for the aqueous solution of HC2H3O2. 79. Okay. HC2H3O2. When you see a formula like that, where you have multiple elements and oxygen's one of them, there ought to be a light in your brain go off. Say polyatomic ions. And this one is a polyatomic. That is the acetate. The acetate polyatomic ion. So if you look it up in your chart, which you will have available, it's a -1 charge. This is +1, so it's written correctly. Now, is it fair to say, well, it's an aqueous solution, okay, right here. Why is that important? Because only in aqueous solutions do we use the naming convention for acids. Now, how do we know it's an acid? Because it has a hydrogen here, 1 or more hydrogens first. That identifies it as being an acid, or potentially an acid. Naming convention for acids, if you put it in water. If you don't put it in water, it's just hydrogen acetate. But if you put it in water, then you use the acid naming convention. So what is the acid naming convention? Well, if it's got oxygen in the polyatomic ion or anywhere in the molecule, you don't say hydro. So you're not going to start the name with hydro. What you do then is you look to the anion half, the polyatomic half in this case, and you say, what is that polyatomic ion? It's acetate. And if you make an acid of it, it becomes 8 become X. So it's acetic acid. And you're done. That's it. So that's why the answer is B. Okay. 80. Na plus represents what? Well, test taking technique. Is it an atom? Well, no. It's actually an ion, right? When you say atom, you could mean this part of it, Na, but the best answer is to actually take a subset of atoms, which is ions, because it's got a charge. So it's either B or C or E. Naval ion? I don't think so. Na is sodium, so it's a sodium ion. What's the potassium ion? Right, it's in the same group as sodium. Potassium is K, so it'd be K plus for potassium. K for kalium, which is Latin for potassium, and A is natrum. Okay, 81. All right, the name for this ion, Hg2, 2 plus. 81. All right, I gave you this one because Mercury is different. It's weird. Mercury never occurs as an ion, a single atom. Never. It's always combined. Well, I take that back. It is, scratch that. Mercury can occur as an ion, single atom. But if it's a single atom, what's the charge or the Roman numeral for it? It would be 2, right? Mercury 2 ion. But now we have 2 of them. So each one can only be a +1. +1 combined makes 2 plus. So Mercury as an ion is always 2 plus charge. But if there's one of them, it's a 2 plus, it's a Roman numeral 2 for Mercury. And if there are 2 of them, it's a Roman numeral 1 for Mercury. So that makes this Mercury 1 ion. Okay. Let's see. What's next? Yep. Oh, we got the whole page here on this one. 82. What's the correct name of the compound that results from the most stable ion for sulfur and the metal ion that contains 24 electrons? All right, this is, take a little detective work. 82. All right, so let's write up here what we're given. We need the correct name and the most stable ion for sulfur. Sulfur ion. What is the most stable ion for sulfur? Look at the periodic table. Okay. Noble gases are neutral. Halogens are -1, to the left, the chalcogens under oxygen are all -2. So sulfur has the most stable ion, is 2-. Okay, now we're going to combine that with what? A metal ion that contains 24 electrons, right? So we're not saying it's a polyatomic. We're saying it's a metal that's combined. Well, it can't be a polyatomic. It's a metal, excuse me. Dumb. A metal ion that contains 24 electrons. Okay, so this one has to be 24 electrons. And now what we're saying is that there's only one of these, and one of those. Okay, so what would this one be? How many protons would it have? Because we need that to find out which element it is. If this one has to be a 2+ to balance that 2-, how many protons? Well, 2 more than you have electrons, so it's 26, right? So look on your periodic table, and 26 says it's iron, Fe. Right? And 1 sulfur. So how do we name that? We name it iron 2+ sulfide. Okay, so that's why the answer is D. All right, 83. The symbol for the rubidium ion is, okay, you need the element symbol for rubidium, plus you need to know what ion it is. What is its charge? So rubidium, find it. It's an alkali metal, first group, means it's going to have a 1+ charge, and the symbol is Rb, 1+. Right. That's why the answer is D. '84. What's the correct formula for barium hydroxide? There's no element by that name. You should know that. So it has to be a polyatomic. You look up the polyatomic, and you find out that this one is OH-. How about barium? Where does barium come from? Barium is an alkaline earth, second group, which means 2+ charge. Okay, now we want to write the formula. Balance the charges, 2+, 1-. So BaOH subscript 2. E gives you the correct answer. All right. 85. Correct formula for lead-4 nitrate. So if we're going to have lead-4 nitrate, you should recognize anything with an A, with the ending like that, ATE, ITE, whatever, is a polyatomic ion. So you need to know, what is the polyatomic? Look it up. There's the nitrate ion. Lead, then, symbol here. What's the charge? 4+. Right? It says so right there. Now balance it. Okay? That's it. So that makes D the answer. 86. The name for the acid HNO2. All right. It's telling you to name it as if it were an acid. That is, it doesn't say it, but you know that it's in aqueous solution. It's in water. HNO2 is derived. There's an oxygen there, so you don't say hydro. There's no hydro to start. You just look to the polyatomic ion here. What is that polyatomic ion first? NO2 is nitrite. Okay, ites become us's. So you say nitrous acid. You're done. So that means D is the answer. All right. This next one should be simple. 87. Since you're going to have the chart with you, with all the polyatomic ions in there, really just have to look this one up. The formula for the ammonium ion. Right? Just look it up. That's it. That one's easy. Okay, let's go to 88. The name for AlOH3. All right, look at these here that have the Roman numerals. Do we need a Roman numeral for aluminum? No. Aluminum hydroxide is formed, that's a type 1 compound because aluminum is a fixed charge. So you never say what the charge is. That's redundant. We know that aluminum is 3+. And polyatomic ions are always fixed charge too. So OH minus is hydroxide. Aluminum hydroxide is it. That's all you need. Two things in naming compounds. You don't want to be ambiguous, non-ambiguity in your naming. So there can only be one possible outcome, one possible name with a formula. And then you don't want to be redundant either. You don't want to muddy the water with unnecessary information. And that's what those with Roman numerals would do, right? Aluminum 3 hydroxide. Well, it's true, the charge on aluminum is 3, but you don't need it because aluminum can only be a 3+ charge. All right, 89. Correct name for an aqueous solution of HCN. All right, this is an aqueous solution. It says HCN should trigger something in your head. There's a polyatomic ion in there. So what is the polyatomic ion? Cyanide. So if this were not in aqueous solution, it would be hydrogen cyanide. But since it is an aqueous solution, and there's no oxygen, we start with hydro. So hydro, and ides become X. Hydrocyanic acid. Okay. That's why D is the answer. 91. Let's see, 91. Am I going to need to write this one? Which of the following is named correctly? So, test taking technique. Look at all these, and they're all unique. So, you find one that's named correctly, and you're done. So, HCl. Is that correct? Hypochlorous acid? HCl, 91. HCl. This, if it's an aqueous solution, this is chloride. It would be hydrogen chloride if it were not dissolved in water. So this is the chloride ion. And now it's hydro. Ides become X. Chloric acid. Right? So that one's false. Can't be. How about this one? HNO3. HNO3. This is the nitrate ion. We have an oxygen, so there's no hydro. So H become X, nitric acid. That one's correct. So we're done. That's the answer. How about this one? Just for kicks. NH3. Ammonium ion. Is that an ion? No. There's no charge there. So even if you don't know the ammonium part, you see that it's not charged. There's no ion. So that can't be right. NH43PO3. Ammonium, that's true. Ammonium here. And PO3. What is PO3? It's not phosphate. It's sort of in that homologous family. It's phosphite. So this would be, and it's got the same charge as phosphate, 3-. So you need 3 ammoniums and 1 phosphite, makes ammonium phosphite. That one's false. H2SO3. Similarly, right, it says it's sulfuric acid, but is it really? H2SO3. Well, we got an oxygen, so there's no hydro, but this is sulfite ion. And ites become us's in naming an acid. So it's sulfurous acid. Okay? That's why that one's false. 92. ClO3 is best described as, what is it? A polyatomic molecule, a polyatomic ion. That's it. It's molecular, but it's not a neutral molecule. It's an ion. And it's polyatomic because it behaves as a single unit in reactions. So here we want to pick the best answer. And the best answer is polyatomic ion. Skip 93 and 95, the correct formula for nickel 3 phosphate. Right, so nickel 3 phosphate. All right, is that name correct? Okay, nickel is a transition metal, so yeah, we need the Roman numeral there. Phosphate, that's a valid polyatomic ion, so we can proceed. So what's the symbol for nickel? Right, has a 3+ charge. Phosphate is a polyatomic ion with 3- charge. So that's it. You only need one of each. NiPO4A. That's it. 97. Sodium chlorite. Sodium chlorite, if you're not careful and you don't read that carefully, you're going to think sodium chloride and write NaCl. But that's not right. Chlorite is a polyatomic ion. Sodium, definitely. Chlorite. So remember when I discussed the families, homologous series of polyatomics, chlorate is ClO3 minus. Chlorite is ClO2 minus. So that's it, without the charges, of course. NaClO2, A is the correct answer for that one. '98. What's the correct name for the aqueous solution of H2SO4? Well, aqueous solution means that this having hydrogens at the beginning is an acid, right? That's why you put the hydrogens first. So you have to know, because it's oxygen, there's no hydro. So you look at what was this called? That is sulfate. And H become X, only we modify it just a little bit to make it sound better. Instead of sulfic, we say sulfuric acid. And you're done. All right, how about 101? The formula for the compound formed from the polyatomic ion NH4 and PO4 3-. Okay, so I made this one really easy. If you form a compound from this polyatomic and this polyatomic, is it 4? Yeah. Since you're given, all you have to do is balance the charges. Right? So you need 3 of these. Since they're polyatomic, you can't mess with these subscripts. Since they're polyatomic, you need 3 of those. 3 pluses balance 3 minuses. So that's why A is the answer to that one. 103. What's the correct name for HCl? Aqueous solution of HCl. Right? What would it be if it were not in water? HCl would be a gas. It'd be a fairly noxious gas too. So it would be hydrogen chloride. And if this is chloride, and there's no oxygen, you say hydro. Change that to ic. Chloric acid. Hydrochloric acid. 105. What's the compound PI3 named? Well, you say, what type is it? Type 1, type 2, or type 3? Right? You got a nonmetal and a nonmetal. It's a type 3. So that means you just need to name how many of each one. So it's phosphorus. Because phosphorus is first, you don't say mono. And then you say tri iodide. Okay. Tri meaning 3. So that's why it's A. Next page. Let's see here. 107. Let's take a look at that one. So what's the name for Pb4 plus? Well, that's an ion, isn't it? So, and where does it come from? It's a transition metal, right? So if we're going to name it, we have to say what the charge is. Otherwise, if we just say Pb is lead, right? If we say lead ion, we don't know what the charge is, because lead could be multiple charges. So we have to say lead 4 ion. All right, 111. What's the formula for selenium trioxide? Okay, this should be a giveaway. If you actually say how many of a part of a compound is, then you're guaranteed it's a type 3. So you look and say, yeah, selenium is in the chalcogen family, like oxygen, sulfur, selenium. It's a non-metal. So selenium trioxide, you just need the symbol for selenium, and you have to put 3 oxygens with it. And that's it. You're done. How about 115 next? Which of the following compounds is not named as an acid? 115? Yeah, 115. So let's see, what are our choices? HCN, aqueous, NH3, aqueous, HCl, aqueous, HNO3, aqueous, H2SO4, aqueous. Okay, they're all aqueous, right? So we got that much done to make an acid. What else are we looking for to identify an acid? We're looking for that leading hydrogen, 1, 2, or 3 usually. I've never seen one with 4. 1, 2, or 3 hydrogens at the beginning of the compound formula, right? There's one, there's one, there's one, there's one, there's not one. So this is not named as an acid. In fact, in aqueous solution, well, actually it is ammonia in aqueous solution. But it will react with water. You know, we didn't say anything about that. Ammonia will react with water. And it actually produces a basic, not an acidic solution. So it's still aqueous ammonia. That's it. But that's because, and that's the answer. B is not named as an acid. All right, 117. What's the formula for gold 1 oxide? Right? I mean, is that correct? Gold 1 oxide? Yeah, gold is a transition metal. So you would say, what's its charge? Well, you look on your periodic table and say, yeah, I found it. It could have more than 1 charge. So you need to know the symbol for gold. AU, the Latin aurum. And it has a +1 charge. And it's combined with oxygen, which has a 2- charge. Right. So you need two of those. So AU2O, C is the answer to that one. How about number 121? Carbonate ion has the formula CO3 2-. What's the correct formula for sodium carbonate? All right. What type compound would that be? Sodium. Where does sodium come from? It's an alkali metal. Right. Sodium. So it has a +1 charge. And you're given this part, right? So that means you need two of them. So Na2CO3 is the correct formula for sodium carbonate. E. How about 124? Which of the following represents the hypochlorite ion? Let's see, 124. All right. You remember that homologous group that I gave you? That's the chlorate ion. And ClO2- is the chlorite. And ClO- is the hypochlorite ion. So ClO- is the answer to 124, hypochlorite. If you combine that with sodium, you get bleach. Sodium hypochlorite is in every house. Every laundry room has sodium hypochlorite in it. Of course, now, most of them also have non-chlorine bleach, which is gentler on colors. But anytime you throw whites in the wash, you dump some sodium hypochlorite in there with them. 125. What's the formula for calcium hydroxide? All right. This goes back to type 1, type 2, type 3. You got a metal and a polyatomic hydroxide. Where does it come from? It's an alkaline earth metal, which means it's a 2+ charge and it's fixed. Type 1 compound. That means you need two of these. Okay? So that makes E the answer. 127. The name for HBRO. Is it an aqueous solution? Yep, aqueous. All right, it's got that leading hydrogen, so it's an acid in water. So what we need to do is, because there's oxygen there, we don't say hydro. We look for, what is this? It's the hypobromite. Hypobromite means hypobromous acid. It's one of those, when I did the chlorate family of polyatomics, I mentioned in the lecture that you could substitute one of two other halogens in there, either bromine or iodine, and follow the same pattern. And that's what we've done here. Instead of Cl there for hypochlorous acid, it's hypobromous acid. Okay, 128. The name for H2SO3. Okay, H2SO3. Number 128. H2SO3. You got an acid. It doesn't say it's aqueous, right? So you look at the possibilities. If it's not aqueous, then we would say hydrogen sulfite. Sulfate has 4 oxygens. Sulfite has 3. Hydrogen sulfite. But that's not one of the choices. It's being named as an acid, so that should tell you that you got to go for the acid form. So this has oxygen. So you don't say hydro. You just say sulfurous acid. Okay. 129. Okay. The correct name for P2O5. Type 1, type 2, type 3. Type 3. A non-metal and a non-metal, you just say how many there are. So the prefix for 2 is di, phosphorus, pent oxide. Okay. So that makes it E is the answer to that one. Okay, 129, let's go. 132, let's take a look at that one. The correct formula for silver iodide. What did I say? 132. Notice that there's no Roman numeral in that name, silver iodide. And I mentioned earlier that you could put a Roman numeral in there if you wanted to, because it's a transition metal. But if you look at your periodic table, you find that silver, right here, there's only one possible charge. So technically, it's a type 1 compound. You don't have to say what the charge is. But you do need to know what the charge is. So you may have to look at your periodic table to find the charge. Silver iodide then would have silver with a +1 charge, and iodine, which is an halogen, with a -1 charge. So AgI is the formula. A is the answer. Okay, let's skip down to a lot of repetition of previous discussions. 140. Okay, the correct formula for lead 2 sulfite. All right, that should be a giveaway. It's a polyatomic ion. So you can look it up in your chart and you find that it's SO3, 2-. Lead has a 2+ charge because of that. So 2+ and 2-, PbSO3, that's it. That's why the answer is E for this one. About 142. The correct formula for the carbonate ion. Well, I gave it to you in a previous problem, didn't we? Previous problem said carbonate ion, and then it gives you the formula. Right? CO3, 2-, which is B. Uh, 143. Let's see, we got some detective work here. A compound contains an unknown ion X. unknown ion. So it's got a charge on it. I just don't know what the charge is yet. And has a formula XCl2. All right, Cl2. Now we're getting somewhere. Ion X contains 20 electrons. Oops. There we go. What's the identity of X? All right. So chlorine is a halogen. It always has a 1- charge. So that means this one has to be 2+, correct? To balance these 2 minuses. 2 times 1- is a 2-. So this one, since there's only one of them, has to be 2+. So if it's got 20 electrons, how many protons does it have? Well, it's got 2 excess, 2 more than the electrons, so it has to be 22 protons. Now we go and look. 22, where is that? Ti, titanium. So the answer is Ti2+ is X. It didn't say what's the element, it said what is X, what's the identity of X. So it has to have the charge with it. 143, 147. All right. We're going to name NaHCO3. NaHCO3. Yeah. Type 1? Yeah, type 1 compound. Sodium is from the alkali metals, always has a +1 charge. But we don't have to say +1. We don't have to say the charge in the name because it's a type 1. What's this? HCO3? Look it up. I mean, it's a polyatomic, so look it up. It's hydrogen carbonate. Right? It has a -1 charge. Right? And that makes sense. This is balanced with that. So we have sodium, hydrogen carbonate. That's the systematic accepted IUPAC name. What we call the trivial name, that is, was grandfathered in from history, is sodium bicarbonate. Okay. So B is the answer. Sodium bicarb. Everybody's got that in their kitchen, right? Baking soda. All right. 147, 148. The correct name for an aqueous solution of H2CO3. All right. 148. Aqueous H2CO3. Right. It's an acid, right? It's in water and it's got those hydrogens. Right? So you need to look, because it's got oxygen, there's no hydro. So you look directly to the anion. It's a polyatomic ion. CO3, 2- is carbonate. The carbonate ion. Eights become X. So it's carbonic acid. Okay? Carbonic acid. 153 is next. NH4Br. NH4 is a polyatomic ion. It's called ammonium. No charge mentioned in the name because all polyatomic ions have fixed charges. Right? And this is the only cation in that group. The rest of them are anions. All the other polyatomics are anions. This is the only cation we're interested in. So NH4 has a +1 charge based on this. That's a -1. So we just say ammonium bromide. Okay, that's it. Ammonium bromide. All right, we're doing good on time. I think we're going to finish. Oh yeah, I just got one more that I've selected. 155. All right. (155). The formula for the compound formed from ammonium and sulfate. So we got two polyatomic ions here. Ammonium and sulfate. What's the compound formed from those two? So ammonium is here. +1 charge. Sulfate is here. 2- charge. Right, so just balance the charges. We need 2 of these to balance 2- there. NH4 parentheses 2 SO4. That's D's the answer. Okay, I think that's it. Yep. The useful information in the same folder as the exam that you want to go in and print out first and keep that with you is it should have this page. It should have the polyatomic ions. In fact, right after class, I'll go check to be sure. And it should have this page. Right. This is this periodic table right here that I've been using is right there. It's kind of on its side. Right. So when you print it, it'll be easy enough to rotate. But that's all the information that you get extra. Just those items for this exam. Now, for subsequent exams, what I generally do is I take, if I have separate tables like this, I add those to it. And if I have extra information to go in this table, right, conversion factors, densities, formulas, that type of thing, I just expand that table. So all of this stuff will still be there plus additional for subsequent exams if we cover new material that can be incorporated in that. Now, how do you know which one's available on the exam? You go look at the review document. Pull out the review document in Blackboard and look at the last pages, and those pages will be available for the exam. Now, if you go in under Respondus Lockdown Browser and you go to take the exam and it doesn't let you open up this useful information document, for the first one, of course, you've already got it printed out. But if on this occasion you go in with the printed document and you see that you can't get access to that document from within Lockdown Browser, that means all the subsequent exams are going to be the same way. So in that case, you need to go in every time and print out the useful information. Now, if it's a periodic table, you already have a copy of that, so you really only need to print out the new stuff. But as long as it's in that useful information document derived from the review document, then you can have it with you. Okay. Okay, so we're about 30 minutes, finished 30 minutes early, it looks like. But if you understood everything that we talked about today, if you can go back and get answers for each of those problems we covered, those are examples, right? If you can do those examples, you know why you're doing them, why it works, then you should be fine for the exam. Any more questions? Okay, so next, what is today? Tuesday? So Thursday, anytime between now and Thursday, the 11th, you can take the exam. And when we come to class on Thursday, we'll jump right into chapter 8, chemical composition. That will be the only chapter for the next exam because it requires some getting used to. So I limited that exam to just one chapter. Okay, everybody good?